Good morning. Today's lesson continues our topic all about the data representation of images and sound, and we're building on what we learned last week about how analog sound waves are represented. So this lesson, we want to be able to remind ourselves about the difference between analog and digital and focus on that conversion process, analog to digital conversion. We want to be able to draw a diagram that represents all of the things like amplitude and sampling and wavelength and things like that, and be able to label it. We want to be able to talk about why analog sound can be relatively accurately represented if you get a decent sound card, but it's never going to be as good as the original because analog is nice and smooth as a signal, whereas digital is only ever an approximation, a simplification, an abstraction. And we want to talk about how we can get better quality sound. I'm making a little project at the moment for my son to be able to take a little MIDI keyboard into school. He's just starting a music club. We've got a MIDI keyboard, but we haven't got a small piano for him to take to the music thing. So I want to take the small keyboard, which doesn't actually make any noise. So I'm trying to program a Raspberry Pi to be a MIDI synthesizer, so it listens out for the control messages like you just pressed a middle C or you've just pressed a low G, and it will generate the noise associated with that key. But it's really low quality sound because of the built-in sound card on a Raspberry Pi. It'd be possible to make it better, but it does the job. We particularly want to focus on how we can calculate the size of a wave sound. So let's see what we can remember. Oh, it doesn't have the answers in here. So analog is the original smooth curve, the actual sound. Digital is the approximation in binary. If we want to go from analog to digital, we have to sample, which means take a measurement at a particular moment in time. But the whole nature of analog is it changes over time, so we have to sample regularly. That's what we mean by measurement of sound. We have to sample it and sample it and sample it and keep sampling it because the volume changes with every sample. If our sample rate can be higher, and remember we measure sample rate in hertz, 1 hertz is 1 sample per second. Usually we sample sound at about 44 kilohertz because that's at least twice as fast as the highest frequency a human ear can detect. And by frequency we mean pitch. So if you're a musician, you'll know high frequency means a wave with lots of peaks and troughs per second, like it sounds high because there's lots of oscillations per second. And a low pitch, a low frequency, has only got a few peaks and troughs per second, and it sounds low. The sound sample is just one measurement over time, and the bit depth is how many bits you use to record each sample, like 2 bits per sample, or 3 bits, or 16 bits. So we want to be able to show a diagram. It'd be nice if there was a diagram. Here we go. This is the analog signal. That's a sample, that's a sample, that's a sample. What are we actually sampling? Well, we're sampling the amplitude, the size of the waveform at a particular moment in time. You can't perfectly reproduce the analog, but you can perfectly reproduce the binary, the digital one, because you can sample this and say this is 0, 1, and this is 1, 0, or whatever you choose, however many bits you use. And then you can send those binary bits down the internet or store it on an SD card or do whatever you want with it. So when you talk about a hi-fi or lo-fi, we're talking about fidelity. Fidelity means how close it is to the original. So you can spend a lot of money on hi-fi equipment, high fidelity equipment, because it means it's close to the original analog. If your original analog was a smooth curve and your digital was not a smooth curve, it's lo-fi. It sounds nasty. It sounds distorted. So I would like you, I will come back to calculating file size. We're on P16 in half term 9. It says to circle the correct responses. It might be easier for you if you just grab a shape, whichever shape you like. A tick would be nice if we can find one. Can't really see one in there, but you can put a star on if you want, or any shape. There we go, a star. And just put your shape in green next to the one that you think is correct. So just a reminder, once you've got a shape, it would be nice if the shape could be nice and easy for me to see, so in green or something like that. And if you hold down Control and drag a copy of it, then Be nice if that worked, wouldn't it? What's going on? There we go. Or just Control C, Control V. So let's go through each of these. Digital is shown in red. That's correct. This is a digitized, quantized version in red, and we have to identify the one that is false. So that's not false. Analog is shown in grey. Well, analog is shown in grey, so that's true, not false. Red is sound, and grey is metadata. Well, both of these are sound. It's just the red one is more noisy. The grey one is sound as well, so that's false, I think. And only the red signal can be stored on a computer. Well, that's true. The red one can be stored on a computer because it can be converted into binary. The grey one can't be stored on a computer because it's analog. You can only store digital signals on a computer. So go through each one. They're carefully chosen questions to identify common misconceptions. So take your time, please. Don't rush. Okay, so let's have a look at activity 2 together. It says complete the diagram to identify the sound wave and label each axis. Use arrows as required and be clear about your answer. So it says we need to identify the sound wave. That's this. It says to label each axis. So we always have time on the x-axis, and that's measured in seconds. And then on the y-axis, the vertical axis, we have amplitude. And amplitude is a measure of volume. It's not the same as volume because, and I'm going to rub this out in a moment, that is high volume, but also a wave down at the bottom is high volume. So it doesn't matter whether it's above the axis or below the axis, how high it is means how loud it is. Then it says complete the diagram using lines, arrows and labels to show a sample interval and an amplitude. Well, it doesn't really tell us enough to be able to do this properly. It's a silly question, but I'm assuming that we sample every time that there is a thing, like a mark on the x-axis. So the sample itself, so we're sampling every time there's a tick on the x-axis. So what are we supposed to label? Show a sample interval. So a sample interval is the time in between each sample. So you measure that in seconds. The shorter that interval, the smoother your digital representation. You don't need to draw this bit, but I'll show you what I mean. So if we only sample at those points, your digital wave is going to look like a staircase, and it won't be as smooth as the original one. So if you want a hi-fi, high-fidelity sound, you reduce the sample interval. Then it says, based on the drawing, answer these questions. State the sample rate. Well, if we've got a sample here, a sample here, a sample here, a sample here, and a sample there, every time there's a tick on the x-axis, then that's going to be 1, 2, 3, 4, 5 samples per second. Which is literally the definition of 5 hertz. 5 hertz, capital H, lowercase z, means 5 samples per second. The sample interval, which is probably what the question was wanting to ask, oops, can't spell, is the time between each sample. So that's going to be 1 second divided by 5, which is 0.2 seconds. So I think the question should have said, state the sample interval, which is 0.2 seconds. So those of you who enjoy maths will spot there is a reciprocal relationship between the sampling frequency and the sample interval. What on earth does that mean? I mean that the sample interval is 1 divided by the frequency. As in 1 divided by 5 is the time taken between each sample, and 1 divided by 0.2 is 5 is the frequency. It's a reciprocal relationship, 1 divided by. All right. Now, state the values for labels A and B, assuming a bit depth of 8. So that means, oh gosh, it's a horrible question. We haven't got any labels on here at all to help us. It's 0 in the middle. It should be able to go down to minus the maximum number, minus 128. And it should be able to go up to the positive number, 127, because it's 2's complement. So what are we on? These ticks, this is such a horrible question. I don't really understand how you're supposed to do that. You can guess it's about 2/3 of the way up and about 1/3 of the way down. Let me pause, I'll check the answers for that one. But we can do this one, state the maximum and minimum values. Some of you got this wrong at the end of the last one, so zone in if you've switched off so far. This is in 2's complement. The maximum value that we can have is going to be 127. The minimum value is going to be minus 128 because it's in 2's complement. What does that mean? 127 is going to be not minus 128 plus 64 plus 32 plus 16 plus 8 plus 4 plus 2 plus 1. That's the maximum positive value you can have. The minimum value is just going to be minus 128 without any positive values. So you must make sure that you're writing this in 2's complement. So I'll give you a few minutes to work through these before we go through how to construct an expression, activity 3. So I'd made some assumptions on the data here. I'd assume that the top of the graph was the maximum value and the bottom of the graph was the minimum value, whereas actually the answers assume that each tick on here is 1. So that tick is 1, that's 2, that's 3, that's 4, 5, 6, and 7. So for B, in denary, that's 7, which in binary, with a bit depth of 8, that just means 8 bits per sample, is going to be 3 bits to make 7, 1 plus 2 plus 4. That makes it 4 bits, 5 bits, 6 bits, 7 bits, 8 bits. And you can do the same for part A. A is 3, so you just need to work out what 3 is in binary, 8-bit binary. Great, so the last bit of theory that we need to put into today is how you can construct an expression to calculate the size of a file. So if you remember a picture, you have to multiply the width by the height, by the number of bits per pixel, and then you can calculate the file size. Here it's similar, it's all multiplication. You do the sample rate, which is the number of samples per second, multiplied by the bit depth, the number of bits per sample, multiplied by the time, as in the length of the sound, which makes sense, doesn't it? If you have a better quality sound, it's going to take up more space on disk because the sample rate is higher. If your song is better quality because you use more bits per sample, it's going to take up more space on disk. And if your recording is longer, 3 minutes instead of 1 minute, it's going to take up more space. So you just multiply them all together to get your file size. So let's look at some examples. I shouldn't really show you the answers. There we go. Construct an expression to show the size of a sound file in kibibytes. Remember, that means we're using powers of 2, so 1024 bytes in a kibibyte, with a sample rate of something, a bit depth of something, and a duration of something. Okay, so the size is equal to the sample rate multiplied by the bit depth multiplied by the length. So the size is going to be, let me draw this because otherwise it will take too long. So what is the sample rate? It is 44.1 kilohertz. That means 441000 hertz multiplied by the bit depth. Bit depth is 16 bits per sample. multiplied by the length in seconds, so 90. You might have to do some conversions if it mentions that it's in minutes. So that is going to give you the total number of bits. If we want the answer in kibibytes, we have to first of all divide by 8, because we want the answer in bytes. And we also have to divide by 1024, because you're always going to write kick my granny to pieces. If you want to go from bytes into kibibytes, you have to divide by 1024, and 1024 to go to mebibytes, and 1024 to go to gibibytes. So that, remember, is different to kilobytes. 1 kilobyte is not going to be used in your exam. That's what you'll see most of the time. But a kilobyte is 1,000 bytes, standard units. And a kibibyte is what Edexcel uses in their exam, which is more accurate. It's used in industry. It's an IEC unit. It's 1,024. So as long as you remember sample rate by bit depth by length and kick my granny to pieces, you'll be fine with this. Thank you. Just to correct my mistake, it's been pointed out there's an extra 0 on here. It's always a good idea to put your commas in so that we can detect this. Sorry about that. 44.1 kilohertz. The K here means 1,000. So 44,100 hertz. Oh, and also just to make it clear, you do not have to work out the answer. You won't have a calculator in the exam. It says construct an expression. It means write down what you would have to put into a calculator. You don't have to do that. So when you've finished your Word document, please save it and then make sure it's uploaded to Half Term 9 Data 3. Half Term 9 Data 3 for me, please.